colliders, status, and prospects. Please.
Thank you, Kumron. So I have to start with a preface, which is that until recently I hadn't realized that Assetti, to give his talk, was like being tricked into a trap, because they told me, come and tell us about the LHC and the FCC and all of that. So fine, I prepared my talk. And then all of a sudden I discovered that we have a discussion session, prospects for string theory, whatever. So I said, what are you talking about? My talk is ready. And they said, no, don't do what you want. So I was happy again, until Thursday. Because Thursday, Kumron came and gave a colloquium on quantum gravity and predictions for our universe. And slide 4 said, it's believed that we have no concrete predictions based on string theory, but in this talk I would like to present evidence and predictions from string theory testable by current experiments. So that was the point in which I knew that I really got into a mess. It was too late because I was supposed to go to Italy. I was in Italy yesterday to give a talk at the 90th birthday of a colleague who's still active. And I had to review during the weekend 70 years of his physics activity to prepare the talk. So I got this out of my mind, but as I was driving back last night from Italy, I said, what the hell, I cannot give my talk to Kumron. So I woke up this morning at 4, and I rewrote my talk from scratch. Which, of course, means that it will be a lousy talk. And it will be a miracle if I keep awake until the end, so stay with me. No, it's okay. I prefer to hit the keys. So, in fact, one of the things that came up in my mind as I was going through these 70 years of my friend's work was what happened 50 years ago, which was 74. And I claim here that 74 somehow signaled probably the greatest before and after discontinuity in particle physics since its beginning. And before, we had, the build-up towards the Standard Model. In fact, up to 73, well, GWS, and then GEM, and then in 73, 71, the renormalizability of gauge interactions. In 73 specific, neutral currents were discovered with a detector that's sitting just down in the court here at CERN. So that established the SU2 cross U1 gauge structure for weak interactions experimentally. Asymptotic freedom emerged as a gauge structure for strong interactions. And then Kobayashi and Masukawa showed that we could get CP violation with 3 generations, and that established, in a sense, the CKM flavor structure. The discovery of charm in 74 established the SU2 cross U1 gauge structure for quarks and leptons, confirming GEM and everything else. So the outcome of this is that by 74, the Standard Model gets firmly established as the framework to understand all known phenomena in particle physics. And then we just needed a few Nobel Prizes to be distributed and further experimental exploration to work out the details, but we were done. In 74, at the same time, and that's why it's really a key moment, grand unification came out, supersymmetry came out, 74, sorry. And then from there, it was just an avalanche, a snowball of BSM going from the discussions of naturalness, compositeness of leptons, you name it. So explosion of BSM model building, phenomenology, and experimental searches. So in 74, at the same time, the Standard Model is declared history. BSM searches become the new virgin territory of exploration, with all of a sudden theory providing guidance to experiments as opposed to what had happened until then. 74, incidentally, as you all know, you must know, is also a transition point for string theory. I selected just one example of what I called the before, paper from Gabriele, is Regge intercepts and unitarity in planar dual models. So this was the time in which dual models, string theory, were used to explain hadronic phenomena. In fact, in the abstract of this paper, one of the reasons why I chose it, there is explicit reference to these tools being used to analyze multi-particle production at the ISR, which was the very first proton-proton collider, again, sitting here on site behind our backs, and NAL, which was the earlier name of Fermilab, NAL, energies. Now, in this paper, 74, there is absolutely no reference to QCD that was, quote-unquote, discovered, that was formulated as a gauge theory for hadron interactions just before, as a possible framework to understand hadron phenomena and their relations to strings and dual models. Nothing wrong with Gabriele, of course, right? This is just a reflection of what was happening, and needless to say, the relation between QCD and dual models for these strings is still an interesting open question. But in 74, there is also the after, which is the paper by Schwartz and Scherk on dual models for non-hadrons. The possibility of describing particles other than hadrons, leptons, photons, gauge bosons, gravitons, by a dual model is explored. Interpreting spin 2 state as a model for a graviton, and then going on with outlining all of the good reasons why since then we look at string theory as a model for the world. So back to this turning point in the context of particle physics, this new territory of ample exploration, whatever happened to that in the 50 years that followed? Absolutely nothing. None of these explorations, guts, compositeness, you name it, has led anywhere as yet. And open experimental puzzles remain open. What is dark matter? What's the origin of neutrino masses? CP violation? What is dark energy? Now, contrary to the times leading to 74, there is no dominant theoretical framework to be taken as an obvious default or benchmark. Now, why did I went through all of these? I mean, framework, that is the key word. This is what inspired, Kumrun's talk inspired for me the other day, because I think that this is really the issue, the lack of a reference benchmark that somehow weakens our ability, at least now, to really use and interpret possible results, anomalies, and things that can come out of data. Using the data we measure to draw conclusions on, say, on string theory requires such a leap, in a sense, of assumptions that only if we put ourselves into some framework can be done. Of course, this is not a criticism to the discussions about the swampland and everything, needless to say, but it's just explaining why I believe I don't feel confident with providing you with concrete guidance as to how to use our data for your studies. I'll give you some examples of how in practice the situation has changed. As you will see, what I prepare now is very, very low level. I decided that there was no point in giving you, the latest measurement of the Higgs branching ratios and our prospects, because maybe that is less interesting. So, example one, in the standard model, there is a relation between the W, the Z mass, and sine squared theta W, the mixing angle, which is fixed at 3 levels. It's a number, it's there. At the quantum level, however, this relation depends on input parameters like the top and the Higgs mass. So when precision measurements of MW, MZ, and sine squared theta were done, they confirm the deviation from 3 levels, therefore from the trivial standard model measurement. So was this BSM, or was it a manifestation of radiative corrections to the standard model prediction? You have a framework, the standard model. So you do the calculation of the prediction in the standard model, and you see that if you fix the top mass and the Higgs mass, which were not known at the time you can match the data. So you're making a prediction for the top, the Higgs mass, and what is the next collider to be built to discover them and verify whether indeed it matches the standard model. And this is exactly what happened. So the moral is that the standard model gave us a framework to interpret results of precision measurements, giving guidance as to how dedicated experiments could confirm the consistency of the standard model or expose new phenomena. Let's come to today. Still in the standard model, we can make a prediction on the anomalous magnetic moment of the muon. All of the parameters enter in it via radiative corrections all the way up to 5 loops level. All of the parameters of the standard model are known with enough precision to really make a compelling comparison against data. As you certainly know, the comparison with the data indicates a 5.2 sigma disagreement. So either the uncertainty on the standard model prediction is completely wrong, which could be true because indications from lattice, as you may have heard, suggest that maybe we don't understand the dynamics of the standard model well enough, or there is no physics. But if there is no physics, it's not like in the days of LEP said, that's the top mass, go see it. Here, we don't know where to go. There are several models which could accommodate this discrepancy in the G-2, but they're very disparate, very different. They're not supported by, really interesting theoretical BSM framework, and in particular, there is no guidance on how to plan an experiment to confirm these results. In the 90s, if you saw an event with jets and missing energy, well, that was supersymmetry. You had discovered the neutralino, you had discovered dark matter, because that was pretty much the only game in town, and it was a very specific prediction. Today, if the LHC sees missing energy and jets, there is SUSY, there could be invisible Higgs decays going to axions, dark photons, and many other things. There could be extra dimensions, and just seeing that signal doesn't tell you anything about that. That is just one of an infinite series of hints that we will need. So after the standard model, interpreting discoveries and pinning down their origin is much harder than just predicting possible manifestations of BSM models, even if we work with a specific class of scenarios. One thing is to say, I have this model, I make this prediction, and this prediction could be seen at that experiment. But if that experiment sees exactly that signal, it doesn't necessarily mean that your prediction was what explains that signal, because many other models could have done that. Higgs vacuum metastability is not, well, we can call it a discovery in the sense that it's not something that we knew before, but having measured the mass of the Higgs and the mass of the top very precisely, we can verify that if you run the Higgs self-coupling, the Higgs to the fourth part of the Higgs spectrum, you run it to very high energy, at 10 to the 11 GeV, more or less, lambda becomes negative, so the vacuum becomes unstable. Fortunately, 10 to the 11 GeV is large enough that, before a fluctuation puts us into that vacuum, it will take 10 to the 100 years. So that's why we say we are in a metastable vacuum. A metastable is, as you see, just one point in that very, very unlikely region of parameter space. So why on earth are we there? Is it an accident, or is it maybe a hint of something? And in the context of the swampland, in the context, of course, of several theories, one could give a justification for why we are there. And Kumrum showed that last week. But from our perspective, it's enough to say anything that happens, you say at 100 TeV, would of course completely change this perspective. In other words, if we want to interpret these to draw conclusions on what happens at the Planck scale, we are making an explicit assumption that we're working in a scenario in which nothing happens between now and 10 to the 19 GeV that can affect the relation between the Higgs potential, the Higgs mass, and the top mass. And that is a big assumption that, for those who work out of data, it's hard to accept. This is another interesting example of measurements that could be done, giving, fantastic, important results on our understanding of the universe and cosmology, but that has to be taken with proper care. And that is, the underlying issue is whether the cosmological electroweak phase transition was first order, second order, or as predicted by the parameters of a standard model, a very, very smooth crossover transition. First order phase transitions have been very useful, first of all, because it might help also triggering the baryon asymmetry of the universe, and it would be interesting because it would give rise to primordial gravitational waves that we could see. So, we try to look for models and see whether they leave any imprint in particle physics colliders. One could explore, for example, models where we extend the Higgs sector by a singlet, and you see up there the class of potential Lagrangians and couplings. There are 6 couplings you can put in. You can scan the parameter space, identify models that give rise to strong first-order phase transition, and then for each of these models, which is one point in the scatter plot, you plot how much the Higgs self-coupling varies relative to the standard model. So the axis goes 1, 1.5, so 50%, 100% deviation, and how much the coupling of the Higgs to the Z boson varies. And you see there 10%, 1%, 1 per mil. And you see we have this very, very broad range. So the LHC might discover that the Higgs couples to the Z boson with a coupling which is off by, say, 6% from the standard model. And that's information we will have. And that, doesn't tell us that we are living in this specific model, and therefore there is a strong first-order phase transition, and therefore we have gravitational waves, primordial gravitational waves, even though for that value of deviation in the Higgs-Z coupling, there are, as you see, the red line, many models of this type that fit. And even in that class of models, if we really want to insist, no, but really it is one of these models, we wouldn't know which one it is, because as you see, there are many models that could give rise to different deviations from the Higgs self-coupling. So we also need to measure the Higgs self-coupling in order to try to pin down. But clearly, much, much more would be needed. So the message here is that redundancy and precision, of course, because here we're talking about precision measurements, are absolutely key features in our, in collider-based particle physics to make progress. Redundancy, because we do need, the moment we make a discovery or detect a deviation from the standard model, it will take a long time and a lot of input data before we understand where we are, unless, of course, there is something absolutely clear. And I just give you this example to show that even when it appears absolutely obvious, it certainly appears obvious to us 50 years later, it's not so obvious how to interpret an observation. This is from a paper that Alvaro de Rúcula wrote a few years back. He did the exercise, in fact, I also did that exercise, which is to go to the PRL volume when the J-psi discovery was, by Ting and Richter was announced, and Frascati. It was free experimental inputs. And after that, there is all of the theory papers, right? And you think that there is only one saying, look, they discovered the J-psi. Maybe not even that, because even the janitors and the librarians at SLAC knew that the J-psi was a CC-bar bound state. No, that's not the case. There are proposals like it's a baryon, anti-baryon nucleus, this, that, even Luciano, whom I see sitting up there, who pretty much invented the charm with Jim there to propose, but in fact he wasn't the CC bar, but he was a Z prime. So this is one example of something that today appears absolutely trivial and clearly it was not. So our program then at the LHC, and especially for the future colliders, builds on 3 pillars: guaranteed deliverables, exploration of discovery potential, and conclusive answers to important questions. The guaranteed deliverables is what we know that we can obtain. We cannot guarantee that we will be making discoveries of supersymmetry or anything, but we can guarantee a few things. We can guarantee that we will improve the measurement of fundamental constants, parameters. We will have a deeper exploration of dynamics of a standard model interactions, for example, in the context of exploring electroweak symmetry breaking and flavor phenomena, QCD non-perturbative dynamics. In general, guaranteed deliverables are what these type of measurements, precision measurements, is really defining or redefining the boundary between established facts and conjectures. And I'll give you an example of what I mean. An established fact is that quarks and leptons are point-like to the scale of, say, 1/10 TeV. The conjecture is that quarks are point-like. In other words, going from a concrete statement that we know the limits of to a generalization. And this boundary, which means going from 10 to 20 to 100 TeV, is shifted precisely by doing precision measurements and by working after what I call the guaranteed deliverables. Of course, any facility should work towards exploring and potentially discovering. And by doing that, maybe it can answer in a conclusive way some questions. We'll never be able to answer definitely to the question of whether supersymmetry exists or not, because if we don't see it, it will always be 1 TeV heavier than we've been able to check. But for example, if dark matter were a thermal WIMP, there would be a very fixed window of mass within which it can be, and very clear interactions that you could have, and therefore, in principle, that's something that we could cover exhaustively and conclusively at a collider like the LHC. In fact, the LHC cannot do it, but the SEC, what we are proposing for the future, would do it. So what are these questions that we are addressing today with colliders? Well, the origin of electroweak symmetry breaking is by far the largest and most significant question. I don't say the hierarchy problem. I see the origin of electroweak symmetry breaking as a question which embodies somehow, contains, is broader than the hierarchy problem issue. And in particular, the issue whether the Higgs is elementary or composite is an important one that we need to address. Whether there are flavor phenomena, including CP violation, beyond CKM, and what is the origin of the flavor structure of a standard model, whether dark matter is a WIMP, as I said, whether the source of neutrino masses is a TeV scale phenomenon. Most likely it's not, most likely it's GAT, the seesaw and everything, but there is a window of opportunities for TeV physics. And then, of course, the usual stuff. Are quarks composite? Is there a Z prime? Are there new families of quark and leptons that you would do every time you build a new collider? In the context of a standard model, we need to improve the precision of all of our measurements, because out of these, all of a sudden, some discrepancy, some deviation could emerge. We've realized that the LHC, I don't have time, I'm running out of time, I had a couple of slides. We realized that we really understand very little of QCD, of strong interactions, when it comes to extreme dynamical regimes like high temperature, high density, collective phenomena driven by the environment, like the multiplicity of particles produced. We know nothing, because we are continuously making measurements that disprove our previous belief. I mean, you compare data against models, and I say models, not first principle calculations. Models mean that you already allowed for, tuning parameters, and it just doesn't match. So there are interesting questions there. And of course, where this comes from is the primary question. Do I have 1 minute left? Yeah, 1 minute. So I will just go quickly through everything I had now. I had some speech about the question of where this comes from, because this is a very trivially the most basic thing that you can write in the context. When Weinberg wrote his model of leptons, he picked these, he didn't ask fancy questions, and he wrote down something, and that something happened to be working, but where he got it from, it's not known, and there are many places where it can come from. I give some story here, but the Higgs could be BCS-like, and we would have that potential. It could come from supersymmetry. We would have that potential, but then the potential would be driven and fixed by supersymmetry and supersymmetry breaking. We need to know. We need to know because we don't. I had a long list, not a long, but I had a list here of few results of various interest from LHC, including few hints for deviations. It's not like you always hear nothing has been seen at the LHC. Well, first of all, many things have been seen. Nothing new in terms of, BSM has been confirmed, but there are several examples of processes which are a bit, on the edge, but more statistics will come. So I wrap it up here with these few words. I didn't really have time to place enough emphasis on the issue of Higgs and electroweak symmetry breaking because, as I said, I completely changed my talk. But I left these as a first point in the conclusion. Understanding the origin of the Higgs and electroweak symmetry breaking is a key task, which only colliders, by the way, to the best of our knowledge, can undertake. We wouldn't know how to do that with underground experiments, with cosmic rays or whatever. Firm and ambiguous experimental evidence of standard model deviations, at least in particle physics experiments, are needed if you want to define a credible BSM scenario around which to develop interpretation and plans for future colliders. This is what I dedicated the first part to. Until then, we can only rely on precision, improved sensitivity, and higher energy to extend our exploration. The diversity of collider phenomenology, especially on the hadronic side, allows us to probe a huge dynamic range of phenomena, challenging the theoretical understanding, both at the level of fundamental understanding as well as computational complexity. And the goal of measuring and theoretically describing standard model data, which means guaranteed deliverables, goes hand in hand with the search for BSM physics, whether directly or via precision tests. And with this, I leave you.
Thanks for a wonderful talk. Any questions for Michelangelo?
Hi, thank you for the fantastic talk. Really enjoyed it. So in the spirit of connecting string theory to this outlook in particle physics, where would you place axions in this picture? Do you think they are a promising avenue? That there's maybe a window we can conclusively rule out or test in reasonable time frames?
Well, first of all, we have to find them. And then once they're found, it will depend on the mass, on the couplings. And from there, I bet that there will be even weirder possible interpretation than what we've seen in the case of a J-psi. It will be a long time. I'm not saying that it will not be possible. In fact, it will be possible, but it will not be immediate. I don't know. Again, in the context of a framework, it will be immediate, because in the context of a framework, if you do have a prediction for an axiom with given properties that is what your model gives, of course, you have a right to claim that your model explains that axiom. But what if there are two of you making the same claim starting from two different models? And to identify precisely what are the areas of non-overlap is very hard, because again, even supersymmetry, when we say the supersymmetry has not been seen, we refer to the minimal SUSY standard model. It's enough to add a couple of singlets, and also all of the limits we have go away. For all we know, there could be a supersymmetric particle at 35 GeV that we haven't seen because it's hard to see, and it's just a singlet partner of the Higgs, right?
Any other questions? Bernard.
Very nice talk. Can you summarize in a few seconds what should we expect from a high luminosity LHC?
In 2 seconds, they're gone.
I give you 30.
It's finished. 2 seconds and gone. The measurement of the Higgs self-coupling to a level at which the plot like the one I showed before become interesting. If you go to that plot and you take 50% precision of the Higgs self-coupling, which is what we aim at, that already has sensitivity. I don't like to say excludes. I prefer to say has sensitivity to a large class of models with strong first-order phase transition.
Any other questions? Daniel?
Yeah, hi. Up here.
Gosh, oh yeah, sorry.
I'm just curious if you have any comments about how things are going with planning for the FCC. I heard some concerning issues about the funding and so on recently, but what's the status?
Yeah, money is never enough. Even if there weren't concerns, they would arise because somebody would be asking for more. So that is an issue. It's a very expensive enterprise. It's, to some of us, it appears like the best bet for the future as a facility, because it replicates what we've seen as being extremely successful. A precisely plus-minus machine that really gives you a solid standing ground on which to build for searches and other, and then the equivalent of an LHC, a Hadron Collider at higher energy. The discussion will take place over the next 3 or 4 years as to whether everybody in the community agrees with this and as to whether it's feasible and viable financially. For the time being, as you said, there is a lot of talk and rumors, but nothing concrete, except the work we are putting into it.
Just want to make one clarification just to avoid misunderstanding. The topic of his talk was not suggested by me. It was by
No, but
by the things
I wasn't claiming that you took me into this trap.
Yes,
I was just saying that somebody for us organized this.
Yes, that's good. Okay, let's thank Michelangelo for a wonderful talk.